We're now into part 2 of esters, and we're going to talk about the hydrolysis of esters using acid and alkali, and we'll talk about the different products which you produce using several different examples. Now, the hydrolysis of esters is done adding water. The definition of hydrolysis is that you either add water, or there is some form of hydrolysis where you add hydroxide, but mainly it is water. So we add water to hydrolyze the esters. And we normally have a catalyst as well. So the catalyst that you can use is hot aqueous acid. But we can also do this reaction with water and an alkali, and they produce different products. So our exam tip is the acid catalyst will form the carboxylic acid and the alcohol, but the alkali, if you're doing hydrolysis with the alkali, will form the carboxylate ion and the type of salt and the alcohol. But don't worry if you don't understand this right now. We're going to talk about it in a bit more detail using the examples. So in order to understand how we can actually hydrolyze esters, we need to first of all look at the creation of esters in a bit more detail. Now, we haven't mentioned this before, but it is actually a reversible reaction to make an ester. So because it's a reversible reaction, it really is important what you add in each direction. So for example, if I want to take this carboxylic acid, this alcohol, and I want to turn it into this ester, and I want this to be most of the product. Because it's equilibrium, I've got to make sure that it's really, really dry, which means there's hardly any water in it. And I'll explain why. Now, if I put H plus in square brackets, that's automatically assuming that that is strong acid, okay? So that is strong in terms of the acid, sorry, not strong, but it's concentrated, okay? So that is concentrated acid. Now, why do we need concentrated acid? Well, it's simply because if you look here, there is water. So I'm making water. So Le Chatelier's principle will tell you that if you make a change to a system, then the equilibrium or the system itself will do the opposite. So for example, if I increase the concentration of H2O and make that really large, the reaction will do something to reduce the concentration of that and bring it back down again, because I've made it really large. So I've put in a load of water and it want to make it really large. And there'll be an equilibrium which it will reach where it's at a level which is right for this reaction. But if I put concentrated acid in, there's hardly any water around. Because there's hardly any water around, okay, the equilibrium will go to the right because there's a low concentration of water. Okay, so, and then when it gets to the point where the water is at the position of equilibrium, it'll stop and you'll get an equilibrium formed where the reaction rates, the forward and the backward reaction rates are the same. Okay, but if I turn that around and I say instead of that, I'm going to put in H plus and I'm going to put the AQ sign by it. And if I put the AQ sign by it, I'm literally saying I'm adding H plus as my catalyst, okay, but I'm basically going to add a load of water at the same time, which means you then increase the concentration of the water. You've made it go up very much, which means it's so high that it wants to react that water and bring it back down again. The only way it can bring the concentration back down again is to react it with the ester and hydrolyze the ester and bring it back this way. So if you use concentrated acid, the equilibrium will be to the right. If you use dilute acid, it will be to the left. Okay, and going to the left is called hydrolysis. Okay, so we're hydrolyzing, we're going to go that way. Now if we hydrolyze, okay, we are really going to just see what the products are. So the products are acid catalyst forms a carboxylic acid and an alcohol. And really important to remember that the acid is H plus, and you can show it as H plus aqueous, as we've done up here, or you can show it as H plus slash H2O. I think it's useful to think of it as H plus slash H2O, and I'll show you why now. So if you look at a slightly more complicated version than what we've done so far, and we look at this ester. Now, if you're feeling confident, try to hydrolyze this ester and see what it becomes. Okay, so what we do is we know it's going to form two products. And we look at this bond here and we say, right, okay, let's just chop it down the bond here, because that's where the hydrolysis is going to happen. So we're going to chop it down there. And we're going to redraw that out. And if we redraw that out, okay, and we're going to go, and there you go, we've redrawn it out. Now, if that is the case, and redraw the other half out, so the other half is going to be like that. That's all I've done, chopped down there, drawn two halves. Okay, and then what I'm going to do is I'm going to say, do it in red this time, just because acid in universal indicates red. Okay, and if you look here, we're going to put the water back in. So I said we're going to think of it as H plus slash H2O. Okay, so H plus. But the first thing is that we're going to do is add the water back in. The water is OH and H. So OH and H. So I'm going to put the OH to form a carboxylic acid. And I'm going to put a H here to form the alcohol. I've put my water back in, and then I need to look at the H plus. So I want to see the H plus, see whether it does anything to these two products that I've made. Well, H plus is not going to react with the carboxylic acid because the carboxylic acid is already an acid. Okay, and it's not going to react with the OH. Hence, it follows our rule. The acid catalyst forms a carboxylic acid and an alcohol. But I would recommend, and we'll go through in further examples, adding the water first and then thinking, does the H plus or does the OH minus in the next case actually react to turn it into anything else? And these are the two products that you get when you hydrolyze an ester with H plus aqueous or H plus slash H2O. But the last thing we're going to do is just name these things. So look at these and see what you think it is. So this is, the OH is in the middle, so this is propan 2-ol. Okay, propan 2-ol. Then we've got this one, which is, if you think of this as number 1, this is number 2, the priority is with the carboxylic acid. So that would be 2-methyl. So it's 2-methyl and then 1, 2, 3 propanoic acid. So 2-methyl propanoic acid. And that is the result of acid hydrolysis. We're now going to look at the same molecule, but this time we're going to do it with an alkali. So we've got alkali over the right here. You see it's OH minus slash H2O or OH minus aqueous. There's water in that hot aqueous alkali. We know it's going to form a carboxylate ion or a salt, and we'll explain that in a minute, and an alcohol. So all we do is the same thing as we did before. Now I've drawn this line already down this ester bond, and I'm going to break it apart. So I'm doing exactly the same as I did before. So we have two products we're going to make, and we're going to have OH minus slash H2O. All we're going to do that side, and I've drawn that, so I've drawn it from that side, and then I'm going to draw it from this side. Okay, so, and there you go. So you have your parts. Now I'm going to add my H2O in the form of OH and H. So there's my H to turn it back into an alcohol. Okay, and there is my OH there. Now here's the really important thing. You've added the water, but now you need to look at the OH minus. Now the OH minus comes from something like sodium hydroxide, and it reacts with acids. So when it reacts with acids, it removes the proton and makes water. So if I just take this now and I remove that proton, okay, and that's then gone. Okay, so we've removed the proton because it's reacted with the sodium hydroxide, and that leaves behind a negative charge. So we've got a negative charge there. So that is called our carboxylate ion. So this here is our carboxylate ion. Okay. So it doesn't, however, react with the alcohol. The alcohol is not acidic enough to react with the hydroxide, and therefore you don't get it. Now, if we change this ever so slightly, okay, and we do this using sodium hydroxide instead. So we're going to do sodium hydroxide instead, and these are slight variations upon a theme. So imagine I had sodium hydroxide aqueous instead, and the question said sodium hydroxide, not OH minus, but sodium hydroxide. I do exactly the same thing, and I'll draw it out again. So here we go, and I will then do the alcohol, and there we go. So we've got the alcohol, and we've got the acid, and we've just split it down the middle. We then put our OH back on. We would put our OH back on, but we know it's reacting with the hydroxide, so we're not going to put the H on. Okay, and we put our H back on there. Now the difference is that the sodium is now mentioned within the question, so therefore you have to include it. So you can put it as O minus Na plus, or you can just put ONA if you want. But in here, the sodium is a spectator ion, so they just haven't included it overall. So really important distinction in the questions. If it says sodium hydroxide, you've got to include this sodium. If it just says hydroxide ions, you can leave the sodium off. So two simple, hopefully, distinctions so that you don't come foul when you do an exam question with these tiny little differences. So we now know how to hydrolyze esters using sodium hydroxide or hydroxide and acid and dilute acid. So let's have a look at a couple of examples. Just make sure that you use the video and stop it and try to do this yourself before I explain. So let's have a look at, first of all, doing it with the acid. Remember, we just break the ester bond, then we add the water as OH and H, the H on the alcohol, the OH on the carboxylic acid, and we get these two products. We then do it with the hydroxide, and remember you add the water again, which still would be those two products over there, but the OH minus reacts with the carboxylic acid to make a carboxylate, but it doesn't react with the alcohol. So if we then do another example, but this time is the hydrolysis of phenol. But first of all, let's remind ourselves how you make or use phenol to make an ester. So you need an acyl chloride, and then you add phenol, and then that will make your phenyl ethanoate there. Okay, and that will make HCl. Now the HCl is a small molecule being removed as a result of two molecules reacting together, therefore this is a condensation reaction. If we then look at the hydrolysis of this, because this is a tricky question, remember I said stop, have a go, and then we look at it in terms of the OH minus first. Now here, you notice that the phenol has turned into something called phenoxide. Now the reason is because phenol is a weak acid. Really good to know, it's a weak acid, and therefore it reacts with an alkali, and then just removes its proton. But the carboxylic acid you produce when you cleave that bond also reacts with the hydroxide, so you get a carboxylate and this phenoxide. If you do the acidic one, you'll notice that you just get your phenol and you get your carboxylic acid, because you're just adding your water back in, and neither phenol or carboxylic acid then reacts with the acid again. But let's look at this, and instead of having OH minus, we use something like sodium hydroxide or potassium hydroxide. So the sodium hydroxide there, now that changes the whole thing. So that changes this. You can't ignore the sodium. So if it's in there, you can't ignore it. You must put it on your minus, because Na is Na plus, and it cancels out the O minus, which is why it looks a bit strange with the previous one, because it's got a minus on it. It's not, the charges aren't balanced. It's because the Na was a spectator ion and we didn't use it. But if they say Na is in the actual question, you've got to use it. Let's just remind ourselves of the equilibrium and the ester and the conditions you have to make an ester and to hydrolyze an ester. So here we have one of our esters, okay, and we know we're making water, it's condensation reaction, and if we want to go in that direction, we'll do reflux and concentrated acid, usually H2SO4 or in brackets H+. If we want to hydrolyze, which is that direction, it'll be H+/H2O to say dilute acid, or you can just put H+ in brackets AQ. And remember, if you increase the concentration of water, as in you put a load of water in, it will hydrolyze back that way.